In the previous lecture on elements of field quantization, we have discussed the classical field equation, particularly the Lagrangian formulation of classical field equation. Actually, we have obtained the classical field equation in terms of Lagrangian of the system, and you can remember that our result which we have obtained in the previous lecture was the functional derivative of Lagrangian L with respect to psi minus del t functional derivative of this Lagrangian L with respect to psi dot. This was actually, and that is equal to 0. This equation is actually called the classical field equation in terms of Lagrangian of the system. Here this del cross actually represents the partial functional derivative. Okay, this was the result, and you can see that actually this result is just analogous to the Euler-Lagrange equation. Okay. Now in this present lecture, our aim is again to discuss the classical field equation, but now we are going to find the Hamiltonian form of classical field equation. So in fact this lecture you can say is regarding the Hamiltonian formulation of classical field equation. You know that Hamiltonian equation, which is a canonical equation, is a very important equation of classical mechanics, and we will see here that in case of field, just a field equation will be obtained which will be just analogous to the Hamilton's canonical equations of motion. Okay. So in this lecture we will try to find the classical field equation in terms of Hamiltonian of the system. Okay. So let us start how to find the Hamiltonian form of classical field equation. As you know, you have definitely studied this Hamiltonian function in classical mechanics, and there is a complete playlist of classical mechanics of my channel. You can watch the videos on Hamiltonian formulation and everything will be clear to you. Okay. So as I have told you that in classical mechanics, this Hamiltonian formulation, this Hamiltonian function h is defined like this. This h, which is just equivalent to h of qpt. You know that q is the generalized coordinates or position coordinates, p actually represents the momentum coordinates, and t is for time. And this Hamiltonian function h is defined as summation over I pi qi dot minus L. Okay. Actually here you know that this, what are these pi? Actually this pi is the conjugate momentum of the coordinate qi. So pi you can say is the momentum conjugate to the coordinate qi. And how this pi is defined, you know, definitely you have studied in classical mechanics that this pi, which is conjugate momentum of the generalized coordinate qi, this is defined like this. This is pi equal to del L by del qi dot. It means the partial derivative of Lagrangian function L with respect to the generalized velocity q dot, that is equal to the conjugate momentum. Okay. This is just the definition of this conjugate momentum. Okay. Now actually these two results, that is if you can say that this is our equation A and this is equation B, these two equations are completely classical equation. Okay. And this is defined for a particle in moving in a phase space. Now with an analogy to these two equations, in case of the field, we can define the conjugate momenta denoted by the symbol this capital Pi, and we can also define what will be the Hamiltonian of the field. Okay? As you know, in case of field, the wave function psi acts like the coordinate. Wave function psi just behaves as generalized coordinate. Okay? And the generalized coordinate will be psi of RT. Okay? And so in the light of this equation B, you can say that the momentum Pi, which will be just a conjugate to the canonical coordinate psi I, that will be defined on the basis of this equation B like this. This is Pi of t equal to partial derivative of L with respect to psi I dot, that is del L by del psi I dot. This equation has been just written on the basis of this equation P. Okay? And in the similar manner, on the basis of equation A, you can define the Hamiltonian of the field. Okay? Instead of this small Pi, we will write this capital Pi, and this Qi dot will be replaced by psi I dot. Okay? And Pi, which is defined by in this manner, you can use it. Okay? So let us see. With the analogy of equation A, the Hamiltonian of the field H of t is defined as summation over I Pi psi I dot minus L. Actually, L here is the Lagrangian of the field. Now, in the previous lecture, while we were discussing the Lagrangian formulation of a classical field equation, then you have seen that actually our phase space is divided into different elementary cells which are called phase cells. And if the volume of the cell is taken very small, or you can say that the distribution of the phase volume is actually almost continuous. So we do not find this h of t in terms of summation. But in actual practice, as the phase space will contain continuous distribution of phase cells, so in the continuum limit, we consider that volume of any phase cell, let us say ith cell, tends to 0. And in that condition, this psi I, which is actually, you say that this is the ith coordinate, that will be just interpreted as that it is the value of the coordinate psi of RT in the ith cell. Okay? In the ith cell. And in this condition, if you will define this Pi of t, you can see what is this Pi of t, you can see it here. Pi of t is equal to del L by del psi I dot, and here L is the Lagrangian. Now, if you want to define the Lagrangian function in terms of Lagrangian density, how you can define? You can see, if we consider that in ith cell, the volume of the ith cell is, let us say, delta Vi, okay? And the Lagrangian density there is this curly L. So this L times delta Vi, this will be actually equal to what? This will be, in fact, the value of Lagrangian in the volume delta Vi. Okay? So at the place of this L, the place of this L, you can see this L, we can write the Lagrangian density times this volume. Because when you say Lagrangian density, that means what? That means the value of Lagrangian per unit volume. So in unit volume, the Lagrangian is this curly L. So in delta Vi volume, the Lagrangian will be this curly L times delta Vi. So this L, which is Lagrangian, can be replaced by L delta Vi. So here I have written that this Pi of t is equal to del L by del psi dot RT times delta Vi. Okay. Now this del L by del psi dot, this is written like pi of RT. And actually this pi of RT is actually known as conjugate field. This is actually the partial derivative of Lagrangian density with respect to psi dot, and this is called conjugate field, and it is also a function of R and T. So instead of this partial L psi dot RT, we have written here pi of RT. Okay. So you can see that this pi of RT is equal to del curly L by del psi dot RT. Here this curly L is what? This is Lagrangian density, you know. And you know that actually when we will write instead of this Lagrangian density, this curly L, if you want to write the Lagrangian of the field, what we will do? We have definitely learned in the previous lecture. One thing here I would like to say you, that if you want to understand each and every step of this discussion, you must watch the video on the Lagrangian formulation of classical field equation first of all, because there will be so many results, so many concepts that have actually been discussed in the previous lecture on classical field equation, that is Lagrangian formulation. So in fact already in the classical field in the video on classical field equation in Lagrangian formulation, I have shown there that if you want to replace this Lagrangian density curly L by the Lagrangian of the system, you must change the partial derivative of this function by the functional partial derivative. When you take this symbol del cross, that is what? That is functional partial derivative. So you can also say that this conjugate field pi of RT is defined like this. This is actually the functional partial derivative of Lagrangian L with respect to psi dot. Okay, with respect to psi dot. Okay. Now pi has been defined like this. Now you can also write the Hamiltonian in this condition. As I have told you that actually the phase cells are almost continuously distributed. So we must think that the volume in phase space is continuous, and instead of this sign of summation in equation 2, we must take integration. Okay. And therefore when you will actually want to define this h of t, this sign of summation will be changed by sign of integration, and instead of this pi we will write this much. This will be pi RT or times delta Vi. Okay. And instead of this L will remain same. Okay. So again you can see that if we want to write this h of t, then what will be actually the result? Actually here this pi of RT dot psi of RT minus Lagrangian density dV integral. When you take integral over V of this much, you will get the Hamiltonian of the system. As you can see that Hamiltonian of the system, if you want to express in terms of the Hamiltonian density, what will be the expression? It means if you consider that this curly h represents the Hamiltonian density, then what does it mean? It means in unit volume the Hamiltonian is equal to this curly h, and so in dV volume what will be the Hamiltonian? That will be this curly h times dV. Okay, and when you will integrate this for the entire volume V, you will get the total Hamiltonian. So here I have taken this curly L, which represents the Lagrangian density instead of Lagrangian, and multiplied by this dV. Okay, and after that we integrate it, so we get the Hamiltonian. So you can see that since the total Hamiltonian H should be equal to integral over V Hamiltonian density dV. Okay, but I have defined this H like this, so definitely you can say that this Hamiltonian density curly H of RT is equal to what? This is pi of RT times psi dot RT minus Lagrangian density, this curly L. Okay, and this curly H, as I have told you, this is actually the Hamiltonian density. Okay. Now you have studied in the previous lecture the classical field equation, which is just in terms of the Lagrangian of the field, and that is analogous to the Euler-Lagrange equation. You have seen that the classical field equation is given like this. This is functional partial derivative of L with respect to psi minus del t functional partial derivative of L with respect to psi dot equal to 0. And therefore you can write that this functional derivative of L with respect to psi is equal to what? This is del t pi of RT, because you know that you have seen this in this equation 4, that this functional derivative of L with respect to psi dot is equal to the conjugate field, this is pi of RT. Okay, pi of RT. So instead of this functional derivative of L with respect to psi dot, I have written here this pi of RT, okay, which is called conjugate field. And del pi by del t, this is simply pi dot. So pi dot of RT is equal to what? This is this is actually functional partial derivative of L with respect to psi of RT. Or you can also say that this is del cross L by del cross psi. Okay. So we have defined both pi and pi dot here. Okay. Now after getting these results, you can see this from this equation number 5, that h of t, which is Hamiltonian of the field, this is given by integral over v this much. So I am just simplifying this equation. You can see h of t as equation 5 reads that this is integral over v pi of RT psi dot of RT minus Lagrangian density this curly L dV. Okay. Now h is defined like this. Now let us take the this is delta variation, or you can say change in h. So if h is defined like this, then what will be this delta h? Delta h, you can see that we will operate this delta variation operator on both of these terms. This is your first term in RHS, this is your second term. Okay. So operating this delta variation operator on first term, you can see, since there is a product of two functions, the first one is pi of RT, second is psi of RT. So what will be your result? You can see this will be integral over V. Now delta pi times psi dot, okay, plus plus pi times delta psi dot dV. Okay, and in the, as I have told you that before watching this video you must watch the previous video on classical field equation in Lagrangian formulation, and if you will watch that video you will find that this delta L, delta curly L, where L curly L is Lagrangian density. Actually we have obtained in the previous lecture that this delta curly L is equal to what? This is actually equal to this much. You can watch the previous video, you will get this result. This is actually the functional derivative of L with respect to psi, delta psi, plus this functional derivative of L with respect to psi dot, delta psi dot dV. Okay. Actually here this functional derivative is actually equal to this del cross L by del cross psi. This you will find in the previous video that this is simply equal to delta L by delta psi. You will find it in the previous, but here we do not need this form. Okay, so I have written this expression for this delta curly L directly on the basis of the result which we have obtained in the previous lecture. Okay, now see that we will actually simplify the RHS of this equation to some extent. So let us see. The first two terms are what? This is integral over V delta pi psi dot plus pi delta psi dot. These two terms are at ease. Now see here, I have taken this integral over V for the entire terms, and you can see this functional derivative of L with respect to this psi. You have just seen earlier here, you can see that this pi dot is equal to functional partial derivative of Lagrangian L with respect to psi. So instead of this functional partial derivative of L with respect to psi, you can write pi dot. So I have written here pi dot. Okay. Again you have also seen that the functional partial derivative of Lagrangian L with respect to psi dot, that is equal to the conjugate fields pi, and so this del cross L by del cross psi dot, this has been replaced by this pi. Okay. Now you can see that this pi times delta psi dot and this pi times delta psi dot, these two terms will cancel out. Okay. So the remaining terms are what? These are integral over V delta pi times psi dot minus pi dot delta psi dV. Okay. So in this way we have actually obtained the expression for delta H using the expression for Hamiltonian in terms of the conjugate field pi and the Lagrangian density. Okay. Now it is clear from this equation 8, if you will observe keenly this equation number 8, you can easily say that this Hamiltonian function h is actually a functional of pi and psi. Don't say function, I am saying functional, and you have learnt in the earlier lectures that if h is a functional of pi and psi, how it is written? Actually, functional are written inside this square bracket. If you say that h is a function of q and p, let us say, then you simply write this small bracket. Okay. But if h is a functional of psi and pi, you have to write in symbol here this square bracket. Okay. So this square bracket represents that h is not a function of psi and pi, but it is a functional of psi and pi. Okay. Now, since h is a functional of psi and pi, so from here you can again find the delta variation of this Hamiltonian function h, and this h will be what? Actually I have written this result again on the basis of the result obtained for the field equation in the Lagrangian formulation in previous lecture. So I am telling you, I have told you several times that before watching this video, for the clear-cut understanding of this concept explained in this video, you must watch the video on Lagrangian formulation for the classical field equation. So I have written on that basis here directly that this delta h is equal to integral over v and functional derivative of Hamiltonian h with respect to psi times delta psi, and plus functional derivative of Hamiltonian h with respect to pi times delta pi dv. Actually here this functional derivative of Hamiltonian h with respect to psi, which is written like del cross h by del cross psi, this is defined like this. This is actually partial derivative of Hamiltonian density. This curly h, this is Hamiltonian density, and this is partial derivative of Hamiltonian density with respect to psi minus divergence of partial derivative of Hamiltonian density h by del gradient of psi, okay, grad psi. And similarly, the functional derivative of Hamiltonian h with respect to pi, this is given as partial derivative of Hamiltonian density h with respect to pi minus divergence of del curly h by del grad pi. Okay. In this way, these two quantities are defined. Okay. Now, you can see we have actually defined the delta variation of the Hamiltonian function of the field h in equation number 8 and also in equation number 10. You can see in this equation 10. So same thing has been defined in two equations. And as you know that these psi and pi are actually the independent variables. Both are independent variables. So in this condition, if you will equate equation 8 to equation 10, then definitely the multiples of these delta psi and delta pi in these two equations must be equal. So let us see here that in equation 8, the multiple of this delta pi is what? This is psi dot. Multiple of delta pi is psi dot. And multiple of delta pi in this equation 10 is what? This is functional partial derivative of Hamiltonian h with respect to pi. So you can write comparing these two equations that this psi dot r of rt equal to functional partial derivative of h with respect to pi. Okay. And again you can see that the multiple of this delta psi in equation 10 is what? This is functional derivative of h with respect to psi. While in equation 8 you can see that the multiple of this delta psi is minus pi dot. Okay. So you can write this minus pi dot equal to functional partial derivative of h with respect to psi. Actually, these are the classical field equation in terms of Hamiltonian of the function. So you can say that these are classical field equations. Classical field equations. Okay. In fact, if you observe the form of these two equations, you can easily recognize that these equations are completely analogous to the Hamiltonian canonical equations which you study in classical mechanics. You can remember that according to Hamilton's canonical equation of motion, you know that Q dot is equal to del H by del P. Okay? And you also know that this minus P dot is equal to what? This is del H by del Q. These are Hamilton's canonical equations of motion. And you can compare these Hamilton's canonical equations of motion with the equations which we have obtained in this equation 12. You can easily see that at the place of Hamiltonian H, in this equation 2 there is actually H. Okay? But where in the classical equation, Hamiltonian equation, there is Q dot. In this field equation there is psi dot, and at the place of P dot there is pi dot. Okay? And at the place of partial derivative, here actually there is functional partial derivative. So these two equations are actually the classical field equations in terms of Hamiltonian of the field. Okay? Now, in fact, in general, if you consider that f is any arbitrary functional of psi and pi, remember, I am not saying that f is a function of psi and pi. I am saying that this is a functional of psi and pi. In fact, in that condition, if you will find the ordinary derivative of this f with respect to t, that is df by dt, which is equivalently written as f dot, that will be equal to what? This is del f by del t plus integral over f and the functional partial derivative of f with respect to psi times psi dot plus functional partial derivative of f with respect to pi dot dv. Okay? In fact, this second term actually is nothing. This is simply the Poisson bracket of the function f and h, and of function f and h. So this f dot is written like this. This is del f by del t plus Poisson bracket of f and h, where h is Hamiltonian. Okay? Actually, the Poisson bracket of this f and h is defined like this. This is integral over v, and this is del cross f by del cross psi times del cross h by del pi minus del cross f by del cross pi times del cross h by del cross psi dv. Okay? So, this is actually the Poisson bracket of the dynamical variable f, which is a functional of psi and pi with respect with Hamiltonian of the field h. Okay? So actually this result will be used in the forthcoming lecture when we will actually study the field quantization. Actually till now in this chapter on field quantization, we have only studied the classical field equation. Now our prime aim of the further coming video will be the quantization of the field. We will actually study the quantization of the non-relativistic field or classical field. We will also study the quantization of the relativistic field, okay, and electromagnetic field. So I hope you have understand each and every step of this concept on Hamiltonian formulation of classical field equation. Okay, so thank you very much.